Hello, Internet. This is Garrig, and this is the causes of and solutions to climate change in under 15 minutes. First off, it's important to understand that all numbers presented here are approximate, because these numbers change a bit every year and, frankly, month. They also change based on how they're measured and organized. Even so, while not very precise, the numbers here are accurate enough for the purposes of this discussion. Cool. So I break down the emission sources into 5 categories, which each break down further. The first category is electricity generation, which is responsible for about 25% of all greenhouse gas emissions. The transportation sector is responsible for under to around 20%, although it's closer to 30 in the US. Non-electrical temperature control makes up less than to about 10%, while materials manufacturing is nearly 25. And then all things fit under agriculture and land use make under to around 25%. The emissions by impact are composed of about 75% carbon dioxide. Another 6 or so is nitrogen oxide compounds, a bit over 1% comes from some specific fluorinated gases. Lastly, around 18% comes from methane, which is highlighted in greenish brown to emphasize that while a potent greenhouse gas, methane has a half-life in the atmosphere about 6 to 12 years long, meaning that if we were to stop emitting all these gases, about a fifth of the observed warming would just disappear in a couple decades or so. Yellow's for stuff now at a lower overall cost than their fossil counterparts, typically at higher quality. Pink is for carbon negative. The arrows show the flow of electricity, hydrogen, and direct bioenergy use. In the category of electricity generation, first up is the single largest subchunk, coal power plants, which are responsible for about 20% of all greenhouse gas emissions, as they currently generate about 36% of electricity globally, though dropping quite rapidly. Fossil gas, methane, aka natural gas, is around 5% as it makes up about 22% of electricity. Under 1% are all the other power sources, the majority of which comes from burning oil products that generate up to 3% of electricity. Note the brownish highlight for the fugitive emissions. These are the methane emissions that literally just uselessly leak out of the fossil fuel industry to make up about 6% of all our observed warming. Around 2% of the methane leaks from coal mines, while the remaining 4% or so are the methane leaks associated with oil and gas industry. So currently fossil fuels make up about 60% of global electricity production, while the 6 families of carbon clean energy make up around 40% and growing fast, but it needs to grow way faster. Today, the fastest growing energy families are solar, particularly PV solar, and wind, fast approaching 5% and 8% respectively at the time of this recording. Most future projections aim for each of them to make up somewhere in the range between 15 and 25% of global electricity generation each in the clean energy near future. The nearer, the better. They are the cheapest ways to make electricity we have, and by far the fastest to build out and set up. They're also very versatile and modular, though in those regards, solar has the edge over wind in all of those regards. Note they back each other up well, because in most parts of the world it tends to be windier when less sunny and sunnier when less windy. Next up, we have hydropower at about 15% of global supply, likely to be between 10 and 25% in the future as the grids expand. While extremely dispatchable and grid flexible, hydro dams are vulnerable to droughts and other water distribution changes. This category also includes the future energy wildcard of tidal power. Nuclear now makes up about 9%, with future ranges of about 5 to 25. And while carbon clean, new conventional nuclear is usually very expensive and particularly slow to build out in most of the world. And the climate crisis is time sensitive. It also has the wildcards of both small modular reactors, which try to improve on those weaknesses, and thorium reactors. Geothermal, while only 0.5% now, is grossly underutilized, largely due to competition with the oil and gas industries for most of the same tools and crews, which becomes a strength as it can employ these people post oil and gas. Even the traditional old tech style of geothermal sites are less than 10% tapped. Developing those gets us to about 5% of global electricity supply. The newer, higher tech, enhanced geothermal systems expands the viable sites to push us well over 10%, while the newer, emerging wildcard tech of advanced geothermal systems goes even farther, aspiring to make it viable most anywhere, including old fossil plant sites, taking geothermal's potential well over 20%. Last is the bioenergy family, currently at around 2.5%, with a future between 1 and 10. These stay limited because if you're ever cutting down trees that wouldn't already be going down for fuel, that isn't carbon neutral. Trees grow back way too slowly. I'm talking waste bioenergy, agricultural waste, lumber industry waste, while sanitary landfills and water treatment plants can be biogas and biomass sources, especially with HTC tech, hydrothermal carbonization. This is where you essentially pressure cook most any organic material into an energy positive, carbon neutral, charcoal like substance that can be used by existing coal power plants with little to no modification. It also makes a liquid bioproduct that you can get carbon neutral methane biogas from, which can go into a natural gas plant, same molecule after all. Meanwhile, biofuels are crop grown liquid fuels, which, while a poor fuel for electricity generation, may have use in other industries. You take all these clean energy families and link them up into modern interconnected grids, often with high voltage direct current HVDC power lines for distant travel with low losses, to flexibly take energy from when and where it's abundant to when and where it's needed. Such a grid should also incorporate plenty of the energy storage families themselves. Batteries are the fastest growing of these families, with many chemistries discussed ad nauseum elsewhere. Suffice it to say, they are super efficient with low losses and hyper responsive, able to supply at the speed of shifting demand. Though it's actually pumped hydro that makes up most electricity storage on Earth, and that also has room for growth. We've also got gravity batteries, compressed air, cryoliquid air, and stored heat systems. Lastly, we have using electricity to split water into hydrogen, which isn't a very good way to store electricity, as its efficiency is typically like around 30% compared to upper 60s to 90s in those others, but hydrogen can be used to do some things that direct electricity just isn't as good at yet. And after all that's full, if you still have excess energy on particularly sunny and or windy days, we shunt that excess energy into direct air carbon capture and sequestration systems to pull CO2 straight out of the sky and bury it. Moving on to transportation, we have road traffic making up around 12% of all emissions, though it's closer to a quarter in the US. Yes, see the bottom line on increasing public transport, micromobility, including walkable towns, and a blanket statement on increasing energy and material efficiency that didn't fit anywhere else. These do play a huge part in this and other categories. That said, the majority of road emissions will be solved by the direct electrification of cars, trucks, buses, road shipping, and everything in between being replaced by EVs. So much can, has been, and will be said on this topic. But for now, it boils down to no matter what way you cut it, this is the best path for this sector. It, like so much else on this list, also cuts down on air pollution. They also feed depleted batteries into static storage, while many newer EVs can be distributed storage, feeding into homes and grids with bidirectional charging. Boats and air travel both make up about 2.5% each and are both harder to address. Although, since nearly 40% of all shipping is just moving fossil fuels around, cut those out of the equation and you make quite a dent. At this point, it looks like biofuels and or carbon-neutral synthetic e-fuels, likely phased in gradually, often mixed in, will cover what EV boats and planes cannot. Though we should use EV boats and planes when possible, note that they are still improving and to unknown limits. Those e-fuels are made by drawing CO2 out of the air and combining it with hydrogen to make artificial carbon fuels. It's super inefficient, like 5 to maybe 20%. For boats, wind systems can be used to cut fuel use, as can just slowing down. And I do have to mention that one can make nuclear-powered shipping vessels, controversial as that is. Hydrogen as fuel is also possible in both industries, though there would be logistical, technical, and regulatory difficulties to overcome. Meanwhile, rail is responsible for less than 1% of emissions. We should finish electrifying this sector, expand it, and use it more, as efficient as it is. Modern space travel makes up a tiny fraction of a percent, which can be decarbonized with green hydrogen, e-fuels, or even biogas. Next up, non-electrical temperature control includes space heating, water heating, some gas-powered clothing dryers, and cooking that all still use fossil fuels, particularly gas. Their individual emissions are tricky to disentangle, so I just didn't. Along with air conditioner and refrigerator chemicals, these make up under to about 10% of all greenhouse gas emissions. The answer here is simple: electrify them all where possible. Space heating is well addressed with heat pumps that can act as both hyper-efficient heaters and cooling systems in one. And don't forget about improved insulation. There are many electric water heating options to replace gas and other fossil based boilers, complete the electrification of clothing dryers, and folks need to embrace the superior tech that is induction cooking, while resistance based electric is still a solid low cost option, and yes, people could still use biomass or biogas fuels for when a flame really is needed. Address those fluorinated refrigeration chemicals and AC chemicals by improving the design, standards, and disposal of these chemicals, ensuring they are destroyed and not leaked, ideally replacing them with less dangerous alternatives. The next nearly 25% is made up of the non electrical direct emissions from the manufacturing of materials. Concrete is responsible for about 8% of global warming. By switching from direct burning of fossil fuels for the heating used to make the stuff to green hydrogen or direct electricity for heat, we solve some 5% of all emissions, and the remaining 3% are probably the single best candidate for on site carbon capture technology. There's also some low to carbon negative alternate chemistries and cement alternatives like hempcrete and mushroomcrete, and there are ways to inject and sequester CO2 into cement. Those options aren't useful in all scenarios yet, but we should use them and other carbon negative construction methods and materials like sustainable wood for wherever they work. Steel is similar at about 7% and can be decarbonized by using green hydrogen in direct iron ore reduction, and then use sustainably harvested biochar instead of coal as the carbon source in arc furnaces to make potentially carbon negative steel. There's also an emerging wildcard tech called molten oxide electrolysis that can go from ore, including lower quality ore, to iron with just electricity. Plastics and their associated chemicals are a bit of a pain. Fortunately, only some 4% of emissions. Ideally, we use way less of the stuff and get way better at actually recycling it. That said, we do have carbon negative options in bioplastics sourced from algae, fungi, or various sources of plant cellulose instead of oil. Aluminum makes up about 2%, while the rest of materials like glass, ceramics, and other metals, and most other things, make up another 3 or so. The answer here is simple: electrify everything you can, use hydrogen if and where necessary, and with biogas and e-fuels as your last resorts. And finally, we come to agriculture and land use, making up under to about 25%. Everything here is presented as a range, since how you count what, like fertilizers, feed, and habitat destruction, makes things a little fuzzy. First is animal agriculture, at around 11 to 14.5%, depending on how you count it. Most of this, 7 to 10, all comes from one animal, the cow, mostly from the methane their digestive tracts produce. We can neutralize most of that by adding Asparagopsis seaweed to ruminant diets, that's sheep, goats, and cows. At 2% of their diets, their methane drops 99%, and at 1, it's into the 80s. We can also cover feedlots to collect their methane and their waste as fuel with that HTC tech. Until low carbon beef is more widely available, I do recommend eating less beef, as 1 pound of most beef results in about 60 pounds of CO2 equivalent, about 10 times as much as chicken or pork. While not necessary for everyone, it should be as cheap and easy as possible for anyone who wants to be a vegetarian or vegan to do so. Also, there are several foods that become carbon negative once you decarbonize agriculture, including seaweed, bivalves like clams, mussels, oysters, and scallops, and most food that's grown on trees, various seeds, fruits, and nuts, as well as carby staples like acorns and breadfruit. Next up, landfills make up some 2 to 4%, while wastewater is around 1 to 2. And both can be covered to collect their methane and have most of their solids processed by that HTC tech into bioenergy resources. Rice is currently between 1.3 to 2.5% of emissions and difficult to truly zero out. Although it's a pretty small segment, we still can reduce it with low methane emitting farming techniques and lower methane strains. Also, diversifying diets around the world reduces emissions while creating healthier diets. The remaining 2 to 10% is mostly made up by the rest of agriculture and all of habitat destruction. To decarbonize agriculture, using green hydrogen instead of methane to make fertilizers eliminates 2% of all emissions. Electrify the vehicles and machinery in the industry using biofuels, hydrogen, and or e-fuels where needed. Stop deforestation and habitat destruction as we encourage reforestation and habitat restoration on land and sea. As it turns out, habitats are typically far more economically viable in the long term as their original habitats than as lumber and new farmland. Shout out to agrivoltaics, where you put solar panels over crops that use partial shade, and to hydrosolar, where you put panels on bodies of water like dams and irrigation canals to reduce evaporation and algae growth, while water cools the panels, increasing productivity. Also, shoutouts to carbon negative regenerative farming, other carbon sequestering farming techniques, and to letting offshore wind farms spawn local habitats off their surface growth. Using all these techniques and technologies doesn't require us to give things up. Instead, we gain a higher quality of life with them, and they help bring the developing world up to a standard of living above what most of us in the developed world currently enjoy. This is the superior way to develop. It's faster, safer, easier, cheaper to build a city without gas lines and petrol stations. The electricity grid is going to be there either way, and it's easier, faster, safer, and cheaper to build it out with modular renewables than with slow to build, expensive fossil plants that make you dependent on constantly buying more poison to fuel. Your population will be far healthier without all the associated pollution, saving money on healthcare costs and lost productivity. Thank you.